Well, hello, welcome again to our journey into linear algebra. In the previous video, we looked at how to take a matrix with the rather strange property that it only has one eigenvalue with geometric multiplicity 1, and to show how we could transform it into what was called the Jordan form by using a P-matrix and building chains. And I did one example of that, and I'll do another example now. You might like to have a go at this yourself if you've worked through the previous video, and then have a look and compare your solution with what I do here. Anyway, here is the worked solution to this. So we're going to start off with this matrix 4 minus 2 minus 1 and so on, and we want to convert this to Jordan form. Now we're told in the question that it's only got one eigenvalue, and so again from the trace, if we add this up here, then we're going to get 6, and if there's only one eigenvalue lambda, then lambda plus lambda has to be the trace, and so that gives us lambda as 2 as the only eigenvalue. Now we look at the eigenspace for this, so we subtract 2 off the main diagonal in the usual way, and this matrix here, if you look at it, this has rank 2 nullity 1, and if you look at the first and last columns, you'll see that this is minus 2 times this one. So if I simply take one of these, none of those, and 2 of those, that will dot product with the top row to give me 0, and it'll work with the others as well. So this matrix up here, A, satisfies our basic conditions. It's at the moment it's got one eigenvalue, and so it's got algebraic multiplicity 3, but geometric multiplicity is only 1. So we now can start building our chain. So we have to take this matrix here and square it, which I've done here. There's no shortcuts for this really. You have to just work out a minus 2i squared and look at the kernel of that one. And I may as well keep that eigenvector here, and then I need another linearly independent generalized eigenvector. And again, if you look at this, it's got rank 1 nullity 2 as it has to, and so we keep the eigenvector, which still works of course, and then looking at these two, if I have one of those minus one of those, that'll cancel. So there's my second linearly independent vector, and this will be our generalized eigenvector. Now we don't need to cube it out, because once we go to the next level up, then we're going to end up with a matrix here of nullity 3, and therefore rank 0, and the only rank 0 matrix is the 0 matrix. And again, I'm going to keep these two vectors, the eigenvector and the generalized eigenvector we had before, and I just toss in anything I like here that's linearly independent to these two, and I generally choose 0, 0, 1 as just the easiest one to pick. So in terms of our onion diagram, which is always worth drawing, as we'll see, it's very useful in larger examples as we move on. So we've got our eigenspace in here, so this thing here is the eigenspace for lambda is 2, and that is spanned by one vector spans that space. We now look at the matrix A minus 2i squared. We look at the kernel of that matrix, and the kernel of that matrix is this section here, which will contain our eigenvector, and there's our second, this is our generalized eigenvector, so that's referring to this vector up here. And then finally the third one is incorporating this one, and the span of these three will give me the generalized eigenspace. So we need to build a chain, so we form a chain. We take the vector in the outermost kernel, which is 0, 0, 1, and we're going to chain inwards to the center by multiplying by a plus 2i. So we do that once, we end up with this vector here. Now just as a double check, this vector is going to be somewhere inside this space in here, and so this one has to be a linear combination of these two. And you can see if you take minus this one and then plus this one, you will indeed get this vector. So you can see, you can double check this one is in the span of these two vectors. and we continue on, we chain into the center, we multiply by 2 plus a plus 2i again. Sorry, that should be a minus 2i, I should say there. Multiply by a minus 2i again, and make sure that's clear. So that's a minus 2i, and so you multiply this by a minus 2i and you get the vector minus 1, 0, minus 2, and that one of course has to be in the eigenspace, so it has to be a multiple of the eigenvector, which was this one here. That was our eigenvector, and this is minus 1 times it. So we use these to build our P matrix. So remember, the order is important. You put this one first. This is my V1, so that one goes there, then that one, and then that one. And so P inverse AP then is a Jordan form, and the Jordan form is going to look like this, with 2 on the main diagonal and some 1s in the off diagonal. So that's again another example of how one deals with matrices with this particular property that only has one eigenvalue and one eigenvector. Before we move on to look at more general situation, I thought we'd actually do a diagonalize. We would do a finding an nth power of a matrix that's not diagonalizable. So here's our matrix A, which is 2 minus 9, 1, 8, and we want to find a formula for the nth power of this one. So as usual, we find the eigenvalue of this matrix, and it turns out it's only got one eigenvalue, which is 5, and you can double check that from the trace. 8 plus 2 is 10, 5 plus 5 is 10, and the eigenspace for this, when you subtract 5 off the main diagonal, the eigenspace is minus 3, 1. So that's again telling me we've got a matrix with one eigenvalue, one eigenvector. So the onion in this case is much simpler. So we've got our one eigenvector here. We're going to need to go to the next kernel out to pick up our generalized eigenvector. So again, when you take a minus 5i squared, this is just going to give you the 0 matrix, because this is going to have nullity 2 and therefore rank 0. So again, I copy down the eigenvector and I just pick anything that's linearly independent with this one. May as well pick 0, 1. And so there's my vector 0, 1 here. And now we chain back into the center. So I multiply this one by a minus 5i, and that gets me minus 9, 3. And again, you can double check, because this must be in the eigenspace. So it's got to be a multiple of this one, and it is indeed 3 times that one. So we put our P matrix, that one goes first, and then the 0, 1 there. And the Jordan form is going to be 5, 5, and with a little 1 up here. So the matrix is not diagonalizable, but it's pretty close. We can get to a Jordan form. And using what we did before, we can get the nth power of the Jordan form. So we just take the nth power of these two. And then we have n choose 1, which is n times lambda, that's 5 to the n minus 1. So there's the nth power of j. In the usual way, a to the n then is p times j to the n, p inverse. So I plonk those matrices down here. This is the determinant here I'm dividing by. And you multiply all this out. I didn't go through the arithmetic here. You multiply it all out and you get this matrix here, which is 5 to the n minus 3n times 5 to the n minus 1, and so on. And again, it is lovely that you can actually calculate the nth power of these non-diagonalizable matrices using the Jordan form. And of course, one can always do a double check on this. If you put n to be 0 into here, you end up with the identity matrix. And if you put n to be 1 into here, I'll leave you to check, you get back to the matrix A that you started with, as you'd expect. So that again gives me a little double check that the answer is looking correct. So that's a couple of examples of that, and I wanted now just to say a bit more formally about these generalized eigenvectors. So to formally define these, I've just talked about them loosely so far. So we can formally define the notion of a generalized eigenvector. And here's our definition. We have A as an n by n matrix, and lambda is an eigenvalue of A, and a non-zero vector V is called a generalized eigenvector of A, corresponding to lambda if A minus lambda I to the kV is 0. That means V belongs to the kernel of this matrix for some k bigger or equal to 0. If k bigger to 1, I should say. If k is 1, then V is an eigenvector. If k is bigger than 1, it's a generalized eigenvector. So in some sense, eigenvectors are generalized eigenvectors, but are corresponding to the k equals 1. The generalized eigenspace corresponding to lambda is the set of all the generalized eigenvectors corresponding to lambda. Well, to get to be a space, it's got to have a 0, so together with the 0 vector. So generalized eigenspace consists of all the vectors V such that this is equal to 0 for some k bigger or equal to 1. Another way of thinking about it is it's the union of all of these kernels. So as an example of this, quick example of this, to find the generalized eigenspace for this matrix here, and again we're given it's only got one eigenvalue to make life easy for us. So here is our matrix A. It's only got one eigenvalue, which again we can see immediately must be lambda is 2. We calculate the eigenspace, which is 1, 0, 2. We calculate the kernel of A minus 2i squared, which is the kernel of this matrix. This is rank 1 nullity 2, so I keep the eigenvector and take another generalized eigenvector in the kernel that's linearly independent with this one. And as before, when we take A minus 2i cubed, this is going to be a rank 0 matrix, so it's the 0 matrix. So again, I keep these two and I just toss in anything that's linearly independent with these two, and there's my generalized eigenspace. It's the span of these three. Now, by the way, you're probably thinking, I hope this is also in fact equal to all of R cubed, because we've got three linearly independent vectors in R cubed, and so they're going to span all of R cubed. You could also write this, in fact I could have done this without doing almost any of the calculations above. I could have said, well, if I'm in R cubed, I may as well just take the three standard basis vectors. So in fact, in this situation, all of these are generalized eigenvectors, and the span of these three would also work. However, this is just following on from what we were doing before. You'd be perfectly correct just to write this or this, but I wanted to again just reinforce the idea of moving out from these, using the onion diagram of moving out to these kernels. So by the time we get to the outermost kernel, we've got all of R cubed here. And so any basis for R cubed will be a basis for the generalized eigenspace. Now that in fact will not happen when we get to more general settings where you've got more than one eigenvalue. Then the generalized eigenspaces, you won't be able to do something quite like this. You'll need to do the calculations above. And so that's why I've done it that way. In the next section, we're going to have a look at what are called direct sums to see how we can glue together Jordan forms, and that will then lead us on to finding the Jordan form of a matrix where you've got more than one eigenvalue.